All right, so we're reviewing 10.1 to 10.7. Obviously, you guys are up to ask questions if you'd like. I know a couple of you came this morning and asked a lot of questions, which was great. If there are a couple that are repeated, I may not go over them, to be honest, just because some of them were lengthy. I might just go into the theory real quick and then stop. Because about 5 or 6 of you there this morning went through a bunch of these already. So I want to do other ones as well. So Juliet, I had up first. Which one are you looking at?
Me?
Yeah.
We went from the homework. I don't know if we did it on Saturday.
That's fine. The homework from 10.7?
Yeah.
10.7, number 9. Did we do that one? No, we did not. All right. So it says the half-life of carbon-14 is approximately 6,000 years, which means that one time unit that halves is every 6,000 years physically. Okay? So it says determine how much of 100 kilograms of the substance remain after 12,000 years. So let's stop and think about this for a second. I think it was this morning that a couple of you asked, can I just use the formula that the book gives for half-life? You absolutely can. But I want to explain to you, because that question, seemed to me a little bit confusing at first, because I was like, we do the same formula, but ours is a little bit different. Let me explain the difference here. So the formula I had you guys derive turned out to be this. Right? Where the book gives you this. It's T over H. Is that what it is in the exponent? Is that correct? Okay. All right. So, this is the exact same formula. Let me explain why. X is the number of time intervals that have elapsed. If I tell you, this problem tells you, the half-life is 6,000 years, and they want to know how much of it is left after 12,000 years. How many time intervals is that? 2. So by that statement alone, X is 2. It's the same thing as putting in 12,000 over 6,000 in the exponent. Okay? It's the exact same thing. So if you're going to use the formula in the book, that's fine. T is the time elapsed, H is the half-life. But if you take the time elapsed divided by the half-life, you get what X is equal to. Remember, X, I tried to give more of a general statement about it. I called it time intervals elapsed. So if one time interval is 6,000 years, and 12,000 years have elapsed, that's 2 time intervals that have gone by, which is where 2 comes from that reason. It's the same formula either way. And then we use the initial amount as, what was it? 100 kilograms. Yeah.
Is it okay if I kind of mix them together again without realizing? Y equals A, and then 1/2. And instead of writing X, I wrote T over H.
So if you want, because remember guys, Y is the current amount, that's what N is. A is the initial amount, N0 means N initial number, initial amount. So these are identical. If you want to replace X with T over H when we do half-lives, by all means, yeah. And part B says after 24,000 years. So if the half-life is 6,000 and 24,000 years have evolved, that's 4 increments, or 4 half-lives, 24,000 over 6,000. But it's a decimal that might be a little bit confusing, right? Like it says after 1 year, what would it be in this case? After Y years, that would be in terms of the variable itself you would answer. You would not have a numerical answer for part C. For part C, it says after Y years.
So for the exponent of T over H, the H stands for the
half-life.
right?
And the T is the time elapsed. Mm-hmm. And if you think about it, time elapsed divided by time per half-life is what X is. Again, this is time elapsed divided by the time per half-life. You get the total amount of time intervals.
In this problem, are they looking for the number of kilograms left over?
Yes, absolutely. It says how much of the 100 kilogram substance will remain. So we're putting 100 in here. A half squared is a fourth. A fourth of 100 is 25 kilograms. Again, that was part A. Okay, part B was after 24,000 years, which would be 4 half-lives. So half this again is 12.5. Half this again is 6.25. So part B was 6.25 as the answer. Part C was a little bit trickier. It said after Y years. Y years. So when we had 12,000 years elapsed, We divide it up by 6,000, we get a number here. And now we don't know how many years elapsed. So put a y up here. Or make this y over 6,000. And then we're going to answer in terms of y. I'll tell you now, I'm not going to ask you a question in terms of y. It does not make it any harder whatsoever. Okay, it's just all function of y. Others? Yes, sir. Yeah, so that was one that we did go over. Number 16 was interesting. I'll give you a quick rundown of this one, Seb. Okay, a quick rundown. It says that we have 50% of sugar left after 2 minutes. So 2 minutes is the? 2 minutes is the what? The H value, the half-life. The half-life. 2 minutes is the actual half-life because half of it is dissolved. And they want to know when 90% of it is dissolved. So the way that Regina proposed to do this, which was very ingenuitive here, okay, very creative, was to say, you know what? Instead of using 90% as a number, she said, if 90% is dissolved, how much is left? 10%. If 90% is dissolved, which is what they want to know, she took this as a half-life problem and said, well, we can use the half-life formula where we're looking for 10% left of what we started with. But the question is, what does x become? Now it's a little bit tricky. So Regina showed us that in reality we're trying to figure out the time it takes, right? After how long. We know that this is going to be, in this case, t over 2. Okay, and the rationale behind this is that it's 2 minutes per half-life. So let's say 10 minutes elapsed. 10 minutes elapsed at 2 minutes per half-life. How many time intervals have occurred? 10 minutes, 2 minutes per time interval, 5. So in reality, no matter what this time is, we divide it by 2 to see what x is. X is the number of time intervals elapsed. So in this problem, since t minutes have elapsed, we don't know what t is, we call it t. But we take the number of minutes elapsed, divided by 2 minutes per half-life, and that'll give us the x value. Now a, in this problem, I have to write an a, on the left-hand side as well. And let me explain this. Really? I can't erase? Sneak an A in there. Okay? So if we start off with 1,000,000, whatever the number is, kilograms or grams of sugar, start with 1,000,000 grams of sugar, at the end I want 10% of that left. So whatever A is starting, it's on both sides. The fact that it's on both sides allows us to do what? Because it's on both sides. Divide by A to start. Okay, and this leaves us with, again, 0.1 equals 1/2 to the t over 2. Now you could solve this several ways. You could convert right to logs, which you can do that, which is fine. Regina saw that it was a 1/2 power, right? This is really a t over 2. So she squared both sides to get rid of the 2. I happen to go right to logs. It's the exact same solution again. Okay, either way you want to do this problem. So if I see an exponent with a variable, I go right to logs every time. If, Regina, I saw like a 3/2 power or a 5/2, I would raise it to 2/5 to get rid of it. But when I see the variable, I go right to logs. You could do it that way, though. It works. So to show you, it's going to be a log, keep the base, 1/2 of the argument, which is 0.1, and that equals t over 2. And it's the same answer Regina would have gotten. She got rid of this half earlier, I'm getting rid of it later. So you can do the log of this, and then multiply by 2 to get t by itself.
So what would you do after getting the log?
Calculator. For this kind of a problem on your math test tomorrow, either it's going to be a multiple choice, and the choices will say log of 0.1 over log of 0.5. Remember change of base formula? So I would use change of base formula here. So if it's multiple choice, you're leaving your answer like this. Okay, there's a good chance I'm not going to have you evaluate. You leave your answer like that. If it involves a calculator, then you absolutely should evaluate. If the part of the test has calculator active, you should probably evaluate this number and get an answer for time. If it's a multiple choice or if there's no calculator allowed, you stop here. You leave your answer in terms of logs. There's no reason to go forward at all.
I was going to say a different question.
Yes, any other questions on this one? Go ahead, Jim.
Can we go over like the rules of like 10-4?
10-4. So 10-4 were the beginning rules, right? Not the secondary rules, the beginning ones? I don't have a list in the book. I just wrote them in my notes, so let me just pull up the... All right, so let's take a look at these rules here. So we've got 7 rules listed. The first rule pretty much tells us when the bases are the same and you have an equation, the arguments are also the same. This is a very useful rule when we're solving equations, especially examples where we condense or expand logs. So for example, for number 1, this can definitely be used, and it will be used for a problem like this. Okay, so a problem like that, I would definitely use the first rule, because once I condense this, I then have log base A and log base A. So whenever I see an equation with a log on both sides, if the bases are the same, I need to condense into one. So the left-hand side is really plus, so I think of that as, plus means multiplication, very good. Right, so again, I see the plus sign here. I recognize that this is one factor, this is another factor. Those factors have to be multiplied. Those arguments are multiplied. And the next line becomes x squared minus 2x equals 8. I drop the log pieces on both sides. It's very similar to equating coefficients. Equating coefficients, very similar. Problem 2, or rule 2. If you have the same base for the log as the exponential piece, you automatically drop them. Let me explain this one. Some students had trouble with this, but now that we know our rules better, I can explain this a little further. Let's say I start with this, okay? And I want to simplify this. What do you do with an exponent when it's inside of the log argument? Where does the exponent always go? Helen? Out in front. Out in front. So this becomes the following now. This becomes A times log base B of B. But look at rule 4. Look at rule 4. What's log base B of B? Just 1, isn't it? So this becomes A times 1, which is just really A. So I'm using rule 4 to help me prove rule 2. Again, rule 4 is that if the base and the argument are the same, you always have a value of 1. So this again becomes just simply A times 1, or A, which brings me back to what I needed. So I'm just proving rule 2 real quick. So for rule 2, just remember to bring the exponent out front, and then you'll have log base B of B, which is just a 1. A times 1 is A. Rule number 3, if I have an exponential raised to the same base as the exponential base itself, it's very similar to this. They're pretty much opposites of each other if you picked up on it. This has the same base as the exponent base. This has the same base as the log base. And in either case, they both turn out to be A, right? So it's the same rule, just written backwards. And we can convert this one if we wanted to. We can convert this to logs and it proves it true. Okay, it proves it true. Now, unfortunately, for your test tomorrow, you guys just have to memorize stuff. You have to memorize it. You really have to memorize it. And if you can't memorize the rules, you've got to make flashcards. Okay, you have to make flashcards for this. But again, number 3, you can convert that back to logs if you want to prove that it's true. But it's a rule. Pretty much this cancels with this. I know it's not obvious, but that's where you get A equals A. Yeah? Okay, that's how when I was in high school, I personally memorized the rules, but I didn't always derive them. So when I saw B to the log B, I knew that those kind of dropped off and I was left with whatever the argument is. If I saw log B to the B, or log B of B to a power, I dropped those two off and I'm left with whatever the exponent is. But in either case, the log base b and the base b kind of cancel each other out in rules 2 and 3. Rule 4 is almost common sense. Convert this to log. Convert this to exponential. B to the 1 equals b. Absolutely. Anything to the 1 is itself. Anything to the 1 is itself. So to prove rule 4 true, convert that back to exponential as c. This would read, the base remains the base, and then this is the exponent. B to the 1 equals b. Absolutely. Here, b to the 0 equals 1. Also true. Convert rule 5 back to exponential. B to the 0 equals 1.
What does it say in rule 3? I can't see.
In rule 3, I just showed the cross-off, the cancellation of them. So, all I'm showing is that those terms kind of cancel each other out. Okay? You don't have to memorize it that way, but when I see rule 3, I think of this b as a base, canceling with the log base a. It's not a real direct cancellation, Eduardo. I don't want you to think about that mathematically, but to memorize the rule, that's an easy way to remember that whenever you have the base of the exponential part, which is right here, equal to the base of the log, those two pieces kind of nullify each other, and you're left with a equals a. Same thing goes for this piece right here.
When the equation you have in red, I have a question about
Mhm.
X can't ever be negative, right?
X can, so let's talk about that actually. We referred to that in class real quick. It wasn't X, it's the argument.
Yeah.
So X could be negative. Because what if the argument is X squared? Then you square it, you plug it back in, you do the log of positive. So what Valentina is asking is this. When you get an answer, you have to check the answer. If the answer makes this or this negative, it is not acceptable. So, for example, let's say the answer to this is x equals 1. It's not. Let's say it's x equals 1. 1 works here, doesn't it? What does 1 work here? 1 minus 2 is negative 1. You can't do the log of a negative number. If you look at your graph of the log, it starts and it's asymptotic to the y-axis, and then it does this. There are no negative x values with the graph of the log. That's a good way to remember that log arguments cannot be negative. If the answer for x is negative 3, then it doesn't work here, and it doesn't work here. But if the answer for x were, say, 3, 3 works here, and 3 works here as well. Okay? So you have to check to make sure that your arguments for any logs in the original statement do not become negative.
What if the base of a log is different from the base of a log? Add them. I can't do that.
It's like having unlike statements. Someone's killing me, guys. I'm sorry. I'm trying to. You can't have unlike statements. You can't have 2x plus 3y and sum them. It's the same thing as the bases there. It's the exact same thing. So log rule 6 tells us that b to some number equals 0. Well, is that possible? Can you raise a number to a power and get 0? Can't. Only 0 to a power gives you 0. So you pick any number. 20 million, 7, 4, 1.2. Raise it to any power. You never get 0 as an answer. So there's no value that can go in here to say b to that power equals 0. Right, Seal? Do you notice how I'm reading this, by the way? That's how I read my log statements. I always do this. I say b to this power equals this. B to this power equals this. B to this power equals this. Because the log is the inverse of the exponential. So when I read it, sometimes I look at it in terms of exponentials also. And then rule 7 is one you have to know. Okay, rule 7 you have to know. If you have a base that's not 10, down here you can't plug in a calculator. So you write it as the log of the argument over log of the base. Both of these with a base of 10. Both with the common log of the base. Alex, go ahead. For logs, exponential, what? For logs? Okay. Let's start with logs.
I just have a question on the other one.
Yeah, good.
What does D stand for?
Does not exist. No answer, no solution. All right, so let's do an example of logs to start, right? Logs are the first one to ask. So let's say, I'm going to use a different color. Oops. Does not matter what I make the problem. You can pick these numbers yourself. One thing I'd mention though if you pick thirds or sevenths, or if you make your log base an odd number, it might be tough with decimals later on. So for your knowledge, I'll give you a heads up. I'll probably make it like a 4 down here, so that it's 1/4 when you use that value. Because if I made that a 7, then it's 1/7. And then if you have to transformations on 1/7, it's like, or you have 1/7, you have to multiply that by 2 and then add 7 to it. It just becomes a little messier, which is not a problem, but I want you to recognize that it can be a little more difficult in that sense. Okay? So we look at this problem, and I think of the parent function. The parent function is just a log function with whatever base I had. So the parent function for this is the following. That's the parent function right there. That parent function comes from it really comes from 4 to the x as a power. It really comes from 4 to the x, from the exponential function. Now, when I do this, I'm going to put x here and I'm going to put y here. I always leave, a spot left for x here. Because if I have a horizontal transformation, it's going to affect x. But the y value can be affected by a stretch and by a vertical transformation. So this is my general table I should be writing pretty much every time. Now, the exponential function, let's put this in the top right. The exponential function would be this. Right, that's the exponential function in the top right. How is the log function related to the exponential function? They are inverses. So, what do I do with those coordinates? Flip them. So this is always going to be -1 for logs. That's always going to be 0. That's always going to be 1 for logs. And then my x values for these are going to be what I had for the y values for the exponential function. So this is going to be 1 over b. Oh, that's not -1/4. This should just be +1/4, sorry. 1 over b, and then 1, and then the b value right here. That's change this up here, please. It should be +1/4. So 1 over b, 1, and b. And it's always -1, 0, 1. And we switch it to the exponential. But now we operate on this log function. What do we do first? What did I tell you? I give you an order in which to proceed here. I give you 3 steps.
You do the y's first, so you multiply the y values each by 2.
Because of the 2 in the front, right? That's a multiplier. It's a scalar factor, so I agree. Let's multiply these by 2. Go ahead, Eduardo.
So then it's -2, 0.
Very good. And then, go ahead, Eduardo. Keep going. You got it.
And then you add 1.
Good. You add the k value. Go ahead. Keep going.
So then it's -1, 1.
So there's my new y values. I'm going to use these when I graph for y. But the question is, what is x? Here's my x right here. Except that there's an h in the process. And this is x minus h. So h is just 3. Right? This is x minus h, which tells me h is 3. This gave me k was 1. This was a was 2. So to my x values, I'm going to always add whatever h is. And since it's x minus 3, I'm adding 3. And that's what I'm going to graph. I'm adding 3 to all of those values for x. So this is my 3.25, comma, -1. 4, comma, +1. 7, comma, 3. Now, it's a log function. Vertical or horizontal asymptote? Vertical, very good. Horizontal is only x. Think about decay. The decay graph, doesn't it do this? And doesn't that mean it's going to teeter off flat? That's a horizontal, isn't it? So the log one is the opposite. It's a vertical. And the vertical asymptote is always going to be written as x equals whatever h is. So in this case, x equals 3. So when I'm graphing this over here, First of all, quadrant-wise, I don't need any negative x's at all. And I need just a little bit of negative y. So let me make this line a little bit closer over here. Okay. Whatever h turned out to be, in this problem h was 3, right? H was 3 from this up here. So I use 3 for x. For exponential, it's y equals k. Y equals k. Regina?
Why did you do the big and blue at the top right?
In blue? What did I do that for? To show where this all came from. Ignore it if it's confusing you. I'm just showing where it comes from. Remember, where do you get these values? Are you memorizing negative 1, 0, 1 over b, 0, 1, 1, and b? These are the exact same thing as those, except flipped. They're flipped. The exponential and the log are inverses of each other, but you do not need what was written there, Regina, at all to do this problem. You don't need it. I was just showing where it comes from. Go ahead.
Oh yeah. How do you know when there's a vertical asymptote when there's a horizontal? Or are there both?
Exponential always has horizontal. Log always has vertical. No matter what problem you have. No matter what. Any log function graphed will have a vertical asymptote. Any exponential function will have a horizontal. And it's always x equals h for the vertical and y equals k for the horizontal.
If it's an exponential with the x values being negative 1, 0, and 1, does that always fall?
And the y values would be the opposite for exponential. You flip them all. All right, so I care about x values up to 7, so I'm going to go by 5. And I care about y values up to 3, so I'll go by 1. Do we see how I'm using the full graph? Some of you still really struggle with this. If your graph doesn't look nice, you're going to lose points. I did not take all points on your last 2 quizzes for those of you that have been drawing lines instead of curves, right? They're all curves here. Your values matter. Look at what I'm choosing as my axis. Why did I go from 0 to 10 on the x-axis? Look at my coordinates. Why did I kind of drop down to negative 1 and go up to only 3? I mean, it's clear why I'm doing this, right? So you have to mimic this. You have to make your graphs look reasonable. Even if I give you a grid, if you don't want to use the grid, draw your own graph like this, that's fine. Or you just scale your grid differently, vertically and horizontally. 1 box equals 1 unit this way, but maybe 3 boxes is 1 unit that way, right? But think about the scale of what you should be drawing. Here's my vertical asymptote. 3.25 comma negative 1 is my first point. My second point is 4 comma 1. And my third point is 7 comma 3. And look at the shape for you linear people out there that keep drawing lines. That's not a line. Come on. Look at the curvature. Look at the curvature. It's not a line. Don't connect these, please. And they only look like lines because your graph scales are not drawn nicely. That's why you're drawing them like lines here. And yes, this should ride along the asymptote. It's asymptotic. This one, we don't know. It's going to keep increasing, but it's not going to have a horizontal asymptote. It's not the same as exponential growth of k.
So this is from 10.4. It's just like simplified as log base half. How do you say it?
Log base 1/2 of.
Of 8. Yeah. And then,
Simplify?
yeah, or like 5.
Yeah. So when you get problems like this and you're not sure what to do, yeah, and you can change your base if you have your calculator, but I'll tell you now, you don't want a calculator on this kind of question. Because what you want to do is say, well, this equals some value, right? That's what this is equal to, some value. Let's call that value something. Thank you. X, M, J, K, it doesn't matter. I'll call it M for now to not make you think you have to use X every time. And mark. Now, if I see this kind of a problem set up, it might be useful to turn this into an exponential problem. Even though we put the exponent as a variable, I get that piece. It might make it work, and let me explain. This is really 1/2 to the m equals 8 when I convert to exponential. Remember, the base remains the base, and then switch these two. So the m comes over, the 8 goes over. Why did I do that? What is 8 as a function of 2? 2 to what power is equal to 8? Alex? 2 to the third, not 1/3. That's all right. And then what is 1/2 as a power of 2. 2 to what power gives you 1/2? 2 to the negative 1. And that whole thing is to the m, isn't it? So I can use what's called equating exponents here. Once the bases are the same, which they are, I can rewrite this as 2 to the negative m equals 2 to the third. Why do I do that? Because a power to a power, I multiply those powers. And then as a result, negative m equals 3, and m equals negative 3. So your answer for the original problem that you started with, which was this, is really just negative 3. Is really negative 3.
Is it okay if you did it by instruction once you have it with like 1/2 of that?
Right here, and you just wrote m equals negative 3? I'll allow it if it's right, but if it's wrong, you're going to get like maybe partial credit for the transformation, but the partial credit you may have gained from these steps you will not get. But if it's right, that's fine. As long as you show this stage right here. I don't want you to do it from the log in the beginning. Because then, I mean, you can type in your calculator. It's not going to be a calculator problem when you have this. It'll be a non-calculator on purpose, so I'll force you to do it. But I still want to see the exponential notation.
On the test, since it's really, this is just a simplifying problem, you don't have variables, you can just like do 3 or 3, right?
Yeah, so technically you came up with that m, right? We made that up. So yeah, the answer is just negative 3. So you're right. Technically speaking, they asked us to simplify this, and the answer is just negative 3. You don't need m equals. Yeah, really good point. Because I made up the variable. We call that a dummy variable. Literally, a placeholder, a dummy variable that you'll get rid of later.
Oh, I just have another.
Okay, let's go to Regina, and then I'll go back to you.
I have 2 questions.
Good?
First one is, when we get points off, we just wrote m equals negative 3.
Like, and didn't do that last thing? Like, and did not do the last thing she said? No, it's fine. If you let it equal m and then write it, I'm not going to take it. Yeah, more, just hit the switch. Okay.
Yeah, it's kind of the same. Log 2 of the cube root of 1/4.
So this is the same thing.
Yeah.
Call this m. 2 to the m equals the cube root of 1/4. 1/4 cube rooted is really 1/4 to the 1/3. Is that agreeable?
Yeah.
And then 1/4 as a power is really 2 to the negative 2. Right? Because 2 to the negative 2 would really mean 1 over 2 squared, and that's what this is, 1 over 2 squared really. Right, remember negative exponent means 1 over. So this is really 1 over 2 squared, which is 1/4, and now this becomes a power to a power. Okay, the next line would simply look like 2 to the m equals 2 to the negative 2/3. So m is negative 2/3. I don't know why I wrote that above. It's the same height. Okay, that's your final answer there. Does that make sense?
Yeah.
Okay, it's the same process, but you have to get rid of the cube root to make it 1/3. You have to convert 1/4 to 2 to the negative 2. Very good questions. Others, before I take another one from Isabella, that's fine. I'm happy to take all your questions, but if others have specific questions they want to ask first. Okay, keep going, yeah.
Okay, so it was one of the condensed problems.
Uh-huh.
Log base 2 of n plus log base 2 of n plus 3. I just didn't know what to do with plus 3.
And it said condense?
Yeah.
Or was it an equation?
It was condensed, pretty sure.
All right, so you just condensed the first two.
And then plus 2.
So-
I just didn't know what to do with it.
Yeah, I mean, you can't really do much with that. I mean, I guess you could make that... Oh, I could see what they might do. Possibly, but that's wild. No. Log base 2 of what number is 3? Log base 2 of what number is 3? It's not going to be an integer value. That's why I'm saying it's wild. But you could technically replace this 3 with log base 2 of some other number, which is equivalent to 3, and then combine those again. Right? If you could figure out what that number is that goes in that spot, then you have all log base 2's, don't you? So if I could rewrite, like, if I could figure out what this way, 2 to what power gives you 3? Anybody know? Like 2 to what power gives you, I don't know. 2 to the second is 4. 2 to the first is 2. It's going to be a decimal between 1 and 2. It's not going to be linear, it's not 1.5. Okay, so what I'm saying is, like, if there's a number here you could figure out that goes in that place, if this worked nicely, but it doesn't. Had this been an 8, 2 to what power gives you 8? What's the answer? 3. So this would have been a 3, and then this would be mn times 3, all with the same log base. So if you could have transformed this into something with the same log base, then you could have gone further, but you can't in this stage. Okay? You can't. So it doesn't work. There's no number that you're going to be able to infer or see as a number. Sure, you can do it in the calculator, but that defeats the purpose of this whole process.
When you're graphing an inverse function,
Uh-huh.
when there's a vertical asymptote, if you put you have to draw a line and just show that the graph goes doesn't ever touches it. Would that
You need to somehow indicate it, whether it's in the statement or on the graph. So when you're doing the problem with either graphing exponential or logarithmic functions, either one of them, you got to show an asymptote either on the graph or at least stated, one of the two. Preferably on the graph and stated, really, if you want full credit for it. If you forget it on the graph, I'll probably take off like a half a point or something. Because the asymptote is important. It shows a limiting factor to the graph. It shows a domain restriction or a range restriction. Right?
I have two questions. They're both 10, 5, 31 is the first one.
10, 5, 31. All right. Log base 4 of 40 minus log base 4 of 5. All right, so a problem like this, we're subtracting two things, right? So I need this value, and I need this value, and then I have to subtract them. So if you want to break this into two statements where like the first one equals n, the second one equals x or something, we have two different things. Or instead, what could you do? Use your condensation of log rules. So because this is a minus sign, what does minus tell me to really do? Divide. So to make it faster, instead of setting them equal, you could set each of them equal as separate variables and do all this work, and that would be fine. But that's a lot easier. Then I get this. And now, 4 to what power gives me 8, right? That's what the question becomes. Call this m like we did earlier. Once you get down to one statement, call that m. 4 to m equals what? Well, we don't really know, right? Can you tell me what the answer is? Anyone? No. I mean, I can't even say it, right? I have no idea. I know 4 to the first is 4, 4 to the second is 16, but 4 to the m is 8. What's m, right? I have no idea what that decimal is. So when you're doing this is your final answer, really. Or if it's multiple choice, you don't see that answer, what is it going to say instead? If it's multiple choice and you don't see that as an answer, what will it say?
Log 8 over log 4.
Yes. Next.
That's what I thought, but it said in the book the answer was 3 over 2.
Well, log 8 over log 4 probably is 3 over 2 in the end, I'm guessing. Is that correct or no?
I did, when I got 4m equals 8, I did 2
Oh.
2m.
Yeah, that's a good point. So what she's saying right now is recognizing that these bases are common bases of 2. So that works too. So if you honestly leave it like this, if it's a multiple choice or if it said something else, so for this one, you could set it equal to m. Right, 4 to the m equals 8. M is 2 squared. Good point, Valentina. And 8 is 2 cubed. Becomes 2 to the 2m equals 2 to the 3. 2m equals 3. So m equals 3 halves. Does that work, what she's saying? So I originally, Regina, I said don't do this because 4 to what power is going to be 8? How are you going to figure it out? But Valentina makes a good point. If you write it in exponential form, it might be more obvious. I didn't write it. If I'd written it this way, I would have seen it. You see what I'm saying? I just looked at this and didn't think about the common base there because I was like, oh, 4 to what power is 8? I had no idea. So that's why I jumped to this. But if you write it out, it might be more obvious because this is 2 squared and this is 2 cubed. It makes life easier for you. You had a second question, go.
47.
47 is a log equation. It says log base 6 of x plus 1 plus log base 6 of x is equal to 1. So what's your question on this? Tell me. Where'd you get to? What'd you do first?
I got the answer, but I didn't know. I got x equals -3 and x equals 2, and I didn't know why you can't have. I checked the back.
-3. Plug it into the log. What we say, you can't have inside of the log ever. You can't have a negative argument. So the -3 makes both of these log arguments negative, doesn't it? If you plug -3, they both become negative log arguments. You can't have them, so you reject the answer. But the other answer was what? 1, you said?
2.
2. And if I try 2, that's positive. 2 plus 1 is 3. 3 is positive. We're good. So it's just a check at the end. Can't have a negative argument once you plug in. Okay, Alex, Mauro, Isabella.
Wait, so if you're graphing an exponential, all you do is just, the only difference, you just follow the same set of steps, step, you
As the log one we just did, except the graph is going to either be growth, decay, negative decay, or negative growth. But the steps are identical except that x is now -1, 0, 1, and y is 1 over b, 1, and b. But the transformations that are identical, Alex. The h value is in the exponent now instead of in the log argument. The k value is still at the end. The a value is still in the front. Okay? Maura, you're next. Go ahead.
Oh, no, I figured it out.
Okay.
The question went out.
Even better. Great.
So back to 31, how I did it, I did log 4, 40 over log 4, 5, and then I thought the logs canceled out, and then I just got 8 as an answer. That
Yeah.
doesn't-
So logs don't cancel. Remember, when you use the rule, you still have a log on the outside. The whole idea is that you're not getting rid of log, you're condensing it down into one simplified log function. Okay? One simplified log. Get it?
Okay, and then it was solved for x, it was log base 2 of the quantity x squared minus 9
Equals.
equals 4.
Solve for x.
Yeah, I think so.
So convert to.
Exponential, and then I did 2 to the 4th equals x squared minus 9.
2 to the 4th is 16, right?
And then I broke it up into difference of perfect squares, so like, then I have
You get this, right? Is that what you get? This is 16 over here. Move 16 over, you get -25.
oh, I did 16 equals x squared minus 9, and then 16 equals x minus 3x plus.
But then the 16's there, right? You got to set, whenever it's a quadratic, you got to set it equal to 0. So start by moving the 16 over and then solve. Are both of these going to work? 5 and -5, do they both work? Do they both work? Do they both work? Why? Because it's squared. Even though this is a -5 and a 5 is an answer, if I plug back in here, then I square a negative, it's positive. So it's still going to be positive 16 no matter what I do.
How come that would be your answer if you could just like add 9 so it's x squared is 25, x equals 5?
Right here?
Yeah.
Yeah, you can add the 9 over and get x squared equals 25. And then the square root of 25 is plus or minus 5. Okay? Practice, practice, practice tonight, please. I did not give you a problem set. Let me give you a hint. There's a chapter test at the end of chapter 10. Probably a good source of work resource. I haven't made the test yet. I'm going to make multiple choice and stuff, and I haven't done it. So chapter tests at the end are definitely good resources to use. Okay?
will you be here after school?
Practice.
Oh,
Yeah, baseball. Assume regular. We got to figure out if the weather's holding up. We got to move. Yeah, the goals are right to move. Yeah, you can't hold your own.
I tried to call out this morning, but I was sick, so I think it's really late. So I was ready to call out.
How do you feel?
Like I'm still like,
I know, but I'm also
Oh.
Poke. Yeah?
yeah.
Confident? Everything's going
I
well?
have to look over the graphics. I mixed up other things. I mixed up. I forgot to switch it.
For exponential
Yeah.
log.
But otherwise, I get it. I just have to remember the numbers.
You know your rules, I know your rules now. Practice tonight. Chapter test. Thanks for telling me, Helen.